Hey everyone, we are looking at something called linear approximations. And first of all, let's get a little bit of vocabulary and notation down. So say we have this curve, that nice little guy, that's our f of x, and then we have a tangent line in red. And then, so if I go from some point x equals c down the road a little ways, I have a change in x. And that's my dx or my delta x. And those are interchangeable. You'll see the difference in a second when we look at y. So then if I look at how, like from the, after that change in x happens, how much my y actually changes, like that distance from the like f of c to f of c plus the dx or delta x, I have that actual change in y here. Versus if I travel along the tangent line, I have this other change in y, that's called dy. And the reason it's called dy, that connects to our dy, dx, our derivatives and our differentials. And you're learning to write. There's another video for writing equations of differentials. Just a reminder there. So dy and delta y aren't the same. They should be close if we have a suitably small dx. And what this does, if we are linearizing, it basically just means that we are approximating the function for values of x close to c using the linear function of the tangent line for that x equals c. So basically, if I need to approximate f of this x, I can use my tangent line and go, close enough. So let's take a look at this in action. So, and these are the same kinds of instructions you're going to see in the book. And this video is to help you with problems 1 and 41 in section 5.2. So first of all, we're writing the linear function L of x that best fits f of x equals root x at x equals 4. This should seem familiar to you because you've been doing this for quite some time. It's just writing the equation of a tangent line. So if we need the equation of a tangent line, we need a point and a slope, right? If we're using point-slope form. So we need a point and the slope. Not news, because that way we can do our y equals m times x minus x1 plus y1. Old news there, right? So getting our derivative, so f prime of x. Remember that if you have f of x as x to the 1/2, that really is, or root x is really x to the 1/2. So the derivative is 1/2 x to the negative 1/2. And if you want to make that a little more user-friendly, f prime of x is 1 over 2 root x, because remember a negative 1/2 exponent would be our square root in the denominator. So we can use this to get our point, our slope. So f prime of 4 will be 1 over 2 root 4, which is a fourth. And then we need a point also, so that would be f of 4, and f of 4 is, of course, is 2. So now we can write the equation of our tangent line, or our tangent line, that linear function L of x. So instead of saying y, I'm going to do L of x equals 1/4 times x minus my x1, which is 4, plus my y1, which is 2. Cleaning that up for use. I know we don't usually do that, but let's do that here. So we have 1/4 x plus 1 when we clean that all up. So here is our linear function that best fits f of x at x equals 4. In fact, I have a graph. So I put this in my calculator already. It looks like this. So when we hit trace and look at 4, we can see that we really are on the same spot for our line and on our function. And it looks to be tangent. And as you can see, when we look at values close to x equals 4, the line and the curve are really close to each other. So basically we're just saying, hey, use that line instead of the curve to make an approximation. So if we use our linear approximation, our linear function to approximate f of 4.1, because like say this is in the land before calculators, could you easily do the square root of 4.1? No, but we can plug it into our line. So f of 4.1 is going to be approximately equal to what L of 4.1 is. And if we plug that in, 1/4 times 4.1 plus 1, and that is 2.025. So that tells us the square root of 4.1 is about 2.025. Just for checking things out here, if we look at our graph and if we're on our curve, if I put 4.1 in, I get 2.048, and then on the line 2.025. So as we can see, that 0.025 is a really, really good estimate for the actual square root of 4.1. It's kind of quaint to do this now because we have the technology, but it kind of illustrates things nicely. Okay, so now another thing you might get asked is, what are the values of dx, dy, delta x, and delta y? So, well, delta x is our change, our dx is looking up at our graph here. Our dx is how much our x changed. We went from 4 to 4.1, so our dx, which is also our delta x, because remember, like, delta x is the actual change in x. The dx is how much x changes on the differential, but those are always going to be the same. So our dx is the same as our delta x, and that is 0.1 because we went from 4 to 4.1. That's the easy bit. And then our dy and our delta y, if we can find those. So our dy remember, is the change in y along the tangent line. So that means, so this is that change on the tangent line. So on our tangent line, we went from the point 42 to 4.1, 2.025. So we can also find, just to show this, we can also find this as the differential, like in the other video. The differential would be 1/2 x to the negative 1/2 dy, as shown in the other video. That's our differential again. And when we have the logic of like, oh, we went from 2 to 2.025 along our tangent line, so we know we get 2.025. But if you plug in our 4, our original x, and our, oops, that's not supposed to be a dy, silly me, that's a dx, because that's our differential, right? Dy equals blah, blah, blah dx, see the other video. And so our dx is that 0.1, and when we do that, we get 0.025, and again, it's how much y changed on the tangent line. Write that down. Okay, now finally our delta y, that's how much y actually changed. So our delta y is going to be that f of 4.1 minus f of 4, which if we throw that in our calculator, we get 0.0248. So these two are really close to each other, but they're not exactly the same. So dy and delta y will be close to each other, but not exactly equal. And again, this is how much y actually changed. And that's on f of x. So then the last bit is error. And that's basically, so looking at our drawing, the error is how far off we are. So, and we find error every single time. It's always delta y minus dy. So it's basically like if you think about doing error in science classes, it's the actual value minus the predicted value. So it's how much y actually changed versus how much we predicted it to change. That's how far off it is. This is not percentage of error, so don't even think about going there. This isn't science class, so it's a little different. So error is delta y minus dy, so we just subtract those two. So 0.0248 minus 0.025, and that is negative 0.000154. Do we have very much error at all? Absolutely not. So again, to recap, when you're asked to find, if you're asked to say what is the, use a linear approximation to estimate kind of thing, that sort of question, you're just approximating a function for values of x close to c. So like going back to our graph, this tangent line is a really close estimate for even if I go out to like x equals 5, I have 2.236 versus on our tangent line 2.25. So still a quite good estimate. So this tangent line can estimate the square root of 5 as 2.25 instead of 2.236. So you wouldn't want to go much further than that, but just to illustrate like, oh, hey, that's still quite close. So that is using a linear approximation. So I would check out the exam, read through the stuff in our textbook in section 5.2. It might help. Also make sure you watch that other video.